Hello everyone, myself Sri Devi, Department of Physics, TKM College of Engineering. This video section on Engineering Physics A covers the second part of Module 5, that is Photonics. So let's start and see what photonics is all about. Photonics is also known as optoelectronics. It is a technology that combines optics and electronics. In optics, we mainly deal with photons, which are the quantum of electromagnetic radiation. Similar manner, electrons play the lead role in electronics. So obviously, the working of photonic devices involve the conversion of photons to electrons or vice versa. Or in other words, it is a conversion of optical energy to electrical energy or electrical energy to optical energy. Thus, the excellent properties of electromagnetic radiation permits the fabrication of highly efficient and more reliable devices in this field. And the photonic technology has thus applications in the field of communication, lighting systems, energy storage, data processing, medicine, etc. Coming to photonic devices. There are many photonic devices based on the above mentioned functionalities. In this chapter, we mainly deal with devices like solid-state lighting, photodetector, and photovoltaic devices. Solid-state lighting system is mainly a solid-state device which converts electrical energy to light energy. Mainly light-emitting diodes, that is an LED. Second is a photodetector which converts light energy to electrical energy, and under this head we will be learning about photodiodes. Mainly Pn Photodiode and Pea Iron Photodiodes we will be learning. And the last one in the list is the photovoltaic devices, which make use of the supreme source of energy, that is solar energy, and convert it into electrical energy. And an example for a photovoltaic device is the most commonly used solar cells. Let us go to the details of an LED. That is the light emitting diodes. An LED is a heavily doped PN junction of suitable material capable of emission of electromagnetic radiation under forward biased condition. We can represent an LED using the symbol shown here with a P-type and N-type region, and the arrows pointing outward indicates the emission of electromagnetic radiation. Now coming to the device structure and working. As you can see here, we have a PN junction diode in the forward biased condition. So the potential barrier width is very small in the forward biased condition. So this forward biasing with very small potential barrier permits a movement of electrons from N region to P region and movement of holes from P region to N region through the potential barrier region. That is a depletion region. So when the minority carrier concentration on both sides of the junction are considerably high, electron-hole recombination takes place on both sides of the PN junction. And this loss of energy occurred during this recombination is emitted as electromagnetic radiation, that is light. Thus, the electrical energy supplied in the form of external bias is ultimately converted to optical energy in an LED. It can be found that the energy of this emitted photon is approximately equal to the bandgap energy of the material. Bandgap energy is usually represented as Eg, and from this relation you can even calculate the wavelength of this emitted radiation. So the bandgap energy can be expressed as Eg is equal to h nu, which can also be written as hc by lambda. So from this relation, the expression for lambda is equal to 1.24 divided by Eg micrometers, where Eg is usually expressed in electron volts. So this particular relation indicates that the wavelength of the emitted radiation depends on the energy gap of the material. Thus, the color of the emitted light depends on the type of the material used for fabricating an LED. For example, if you take a gallium arsenide based LED, the emitted radiation will be in the IR region because the bandgap energy of the material is 1.45 electron volt. Suppose if you are taking a gallium arsenide phosphide made LED, then the band gap energy of the material is 3 electron volt, and as a result of that the emission will be in the yellow region. Whereas if you take gallium phosphide LED, you will get green emission because of the band gap energy value of 2.25 electron volt. So this clearly indicates that the color of emitted light depends on the type of the material used for fabricating an LED. Now coming to the features of an LED. Obviously it is a point source of light, and simply by adjusting the current flow through an LED, the intensity of light can be controlled in an LED. Moreover, you need to supply moderate input power, so there is less power consumption in an LED. Also, LEDs possess smaller size and longer lifetime, which makes them compatible with the current IC technology. Also, they are faster in switching, and moreover the materials used for the PN junction fabrication can be selectively varied to get the desired wavelengths. So wavelength can be controlled in an LED. So these are the major features of an LED. Coming to the applications of an LED, I will say you can find it everywhere. Like you can use them as a light source in an optical fiber communication system. They are used as digital displays in modern electronic devices. Also we use them as bulb in our homes as well as in industries. They are used in automobiles, mobile displays, and also they are used in traffic light signals. So these are the major applications of an LED. So that was all about LED. Now coming to the second photonic device, that is the photodetectors. A photodetector is a device which converts optical signals to electrical signals. The essential requirements of a photodetector are its high sensitivity, high reliability, short response time, and low bias voltage. Examples of photodetectors are mainly photodiode and phototransistors, but we will be learning about the details of photodiodes alone in this section. So photodiode, what is a photodiode? It is a reverse biased semiconductor device which absorbs light energy and converts it into electrical energy. The main feature of a photodiode is that they are transparent enough to let light reach the delicate parts of the device. The symbol of a photodiode is shown here with arrows pointing inward, which indicates that the device absorbs light energy and converts it into electrical energy. There are different types of photodiodes available based on its construction and functions, and they are Pn Photodiode and Pea Iron Photodiode. Pn Photodiode is also known as junction photodiode. So we will learn more about Pn Photodiode and Pea Iron Photodiode. First let us see what is a Pn Photodiode or junction photodiode. Pn Photodiode is a reverse biased PN junction with a very thin transparent P region to absorb photons. In reverse bias, as you all know, the P region is connected to the negative terminal and N region is connected to the positive terminal. As you can see here in this figure, there is a lightly doped P region and a heavily doped N region, and the space between the P and N regions is the depletion region. And also a part of the front area is coated with an anti-reflection coating. Mostly it is made of silicon nitride to avoid the unwanted reflections, and the remaining portion is coated with a layer of silicon dioxide. This is about the device structure of a Pn photodiode. Now coming to the working of a Pn photodiode. In the absence of external radiation, that is when you don't supply any external radiation, the device behaves exactly like an ordinary reverse biased PN junction with a wide depletion region. At this time, there is only the reverse saturation current contributed by the minority carriers, and this current is referred as the dark current in a photodiode. This dark current is usually represented as I0, that is I suffix 0. When incident lights hits this arrangement, that is upon irradiation, The photons with an energy equivalent to the band gap energy of the material strikes an atom in the depletion region, and an electron is released from the valence band to the conduction band. This creates a hole in the valence band and a free electron in the conduction band. Thus, large number of electron hole pairs are generated, and this contributes to the reverse current called photocurrent in a Pn photodiode. Actually, this occurs by the movement of electron hole pairs to the opposite terminals of the external bias. Thus, the total current in a photodiode is a sum of dark current I0 and photocurrent Is. So, the total current IL is equal to I0 plus Is. Also, we have to make sure that almost all the photons are absorbed within the depletion region to get maximum current. So, during the fabrication of a Pn photodiode, the width of the depletion layer must be large in order to get maximum current. The second type of photodiode is the Pea Iron Photodiode. The Pea Iron Photodiode is similar to the Pn Photodiode, but here a very lightly doped and wide intrinsic semiconductor layer is placed between the heavily doped P and N regions. As you can see here, there is an intrinsic region between the P and N type regions. The width of this intrinsic region normally ranges from 10 to 200 microns. When a reverse biasing is applied across the terminals of this device, the depletion region extends throughout the intrinsic region, and as a result of that, there exists a large depletion region, and this consequently result in the higher photon absorption rate, and this results in high photon current, high efficiency, speed and sensitivity compared to a normal PN junction photodiode. So this ultimately indicates that the efficiency of the Pn photodiode is resulting from the wide intrinsic region present in this Pn photodiode compared to a Pn photodiode. Now coming to photovoltaic devices, that is solar cells. Solar cell is a PN junction device which make use of the photovoltaic effect to convert solar energy to electrical energy. So what do you mean by photovoltaic effect? Photovoltaic effect is the phenomenon of production of an EMF across a junction of two dissimilar materials. Dissimilar materials, for example, semiconductors, when it is struck by light or other electromagnetic radiations. So when some electromagnetic radiation stuck across a junction of two dissimilar materials, it will ultimately convert the solar energy to electrical energy. So solar cell is a photovoltaic device. Coming to the structure of a solar cell, as you can see here, it consists of a heavily doped PN junction which acts as the energy conversion layer. And also there is an anti-reflection coating made on the top layer, that is above the N-type region, which minimizes the loss of light by reflection. The anti-reflection rail is typically metal oxides like silicon dioxide, TiO2, tantalum oxides, etc. In addition to that, two electrical contact layers are present to carry the electric current out to an external load and back to the cell. These two electrical contact layers are comprising of two things, that is a metallic front grid pattern and a metallic back contact layer. As you can see in this figure, the shaded grid pattern seen at the front face of the cell constitutes the metal contact, that is a metallic front grid pattern. The one in orange color, that is a metallic front grid pattern. And the metallic layer which covers the entire back surface of the cell forms the metallic back contact layer. The part of the solar cell in the back side, which is in black color, that forms the metallic back contact layer. And these two constitutes the, that is metallic front grid pattern and metallic back contact layer consist of the electrical contact layers in a solar cell. So this is the structure of a solar cell. Now coming to the working of a solar cell. When light falls on a solar cell, photons with light energy reaches the junction region and a valence electron is liberated from the parent atom. This results in the generation of free electrons in the conduction band and holes in the valence band. These free electrons and holes are collected on each side of the junction due to the built-in electric field present in the PN junction. Thus, a voltage is generated in the solar cell. Normally, a single solar cell can generate an output voltage of 0.6 volt. Now, these minority carriers, that is the light generated carriers, move across the junction through the external load and generate an electric current in a solar cell. Thus, the basic steps involved in the operation of a solar cell are generation of light generated carriers, collection of light generated carriers across the junction, voltage generation, and finally the output current generation. These are the four major steps involved in the working of a solar cell. Now coming to the IV characteristics of a solar cell. As you all know, the IV characteristics means the current voltage variation of a solar cell. So it is shown here. When no load is connected in the solar cell, the voltage corresponding to zero current is called the open circuit voltage, that is represented as VOC. So when no load is connected in the solar cell, the output voltage corresponding to zero current is known as the open circuit voltage VOC. Also, if the terminals of the solar cells are shorted together, a short circuit current flows through the solar cell with a zero voltage, and this particular current is known as the short circuit current, represented as ISC. So these are the two major parameters used in an IV characteristics, that is open circuit voltage and short circuit current, represented respectively as VOC and ISC. Also, the output power is obtained in a solar cell when load is connected and the respective voltage and current are at its maximum power points. So at this time, you will get maximum voltage and current in a solar cell, which are designated as Vmax and Imax. That time you will obtain an output power in a solar cell. So you can identify these terms from your IV characteristics of a solar cell. So that was all about the photonic devices like an LED, photodetector, and the solar cell. So thank you all.